Hey, Dylan.
Morning, how you doing?
All right. Do you go by Dylan or the
Yes.
okay. I saw something like Jason or something like that on
Yeah,
your
my first name's Jasper. I go by my middle name, Dylan.
just got you. Cool. Yeah, I knew it was something J that wasn't the normal. So yeah, that
Yeah,
I was hoping you also got my code that you were the requestee. It was like,
yeah.
crap, he's gonna show up at 10:20. What can I help you with, sir?
Um, I guess I saved or I did like little screen captures of some of the problems that I was having issues with, so I could share my screen and just show you those.
Let me I got it. There you go. It should be able to allow you to share screen now.
All right, so is it showing up like a Word document?
Yes.
Okay.
It's showing up a yeah, photo submersion of Word document.
Yep. Okay, so uh
Shouldn't say submerged, but
if I yeah, the ones that I circled in red is since I've gone back and like re-looked at them, is what I'm thinking the new answers
oh, gotcha.
should be. But since it's hard to get the problem again to figure out if I had it right.
Right. So it says two objects are dropped from a bridge in an interval of 1 second apart during the time that both objects continue to fall, their separation. So you get to ignore that first second. And then, of course, the equations that tell you how far from where the object was let go
Hmm.
is the x equals 1/2 at squared plus v zero t plus x zero uh, equation. So you see that basically the distance between them would be the distance of the first one minus the distance of the second one.
Uh-huh.
And both of those would be the distance of the first one would be 1/2 a parenthesis t plus one close parenthesis squared. And then the second one would be 1/2 a t squared.
Uh-huh.
So they just differ by basically 1/2 a. So it shouldn't be that they're distances.
Because I had stays constant, but it was incorrect. Because I figured that they would stay constant, one would just be a second behind.
Right. Well, let me actually write out the equation and look at it. So I'm literally taking the x1 and accounting for the fact that it had a 1 second start by saying that time is t plus one. So x1 is equal to 1/2 g times t plus one squared, and then x2 is equal to 1/2 g t squared. I see what's going on here. So this looks like something where I definitely want to write it out for you. So I'm going to pull up my iPad
Okay.
and share that with you real quick. Whoa, wrong thing. No, if I can find my good notes. There we go. Okay. So what I'm going to do now is do share screen. Sorry about that. Took a little bit to catch up to speed. You'll see what you missed just as soon as I show it to you, and then you'll be like, oh, stupid head. So you'll see. Or at least that's the way I am after I discover I've been haven't figured something out. We have a rule that we use in physics that basically says, all problems are infinitely difficult or impossible until you solve them, then they're trivial. So
That sounds pretty accurate.
yeah. So what I was saying earlier is you would call x1 the distance from the top to the first object that fell would be 1/2 g t plus one squared, and then x2 would be 1/2 g t squared. Do you agree that both of them will be obeying that?
So because it gets a 1 second head start, it gets a plus one to the time.
Exactly. Now the separation, which you might want to call delta x, is going to be x1, in this case, minus x2. In fact, since I try to tell you guys the golden rule is when you're using a delta, make sure it's final minus initial. This is exactly the opposite. So I'm going to use that version of delta. Actually, I think that's even sigma. Come to think, actually, it might be a delta. I can't remember. Anyways, I'm going to use it like that. So that's x1 minus x2. But what you might not be seeing is the fact that you got to actually square that binomial. So you're going to get 1/2 g times t squared plus 2t plus 1 minus 1/2 gt squared, which you can now see once I distribute that, I got 1/2 gt squared plus gt plus 1/2 g minus 1/2 g t squared. So you see those two cancel
So
out.
where in the parenthesis, where did the where did the 2t come from? Oh, is it you did the FOIL method for T1,
Exactly.
correct?
Yeah,
Okay.
FOIL
Okay.
method. Yep. So that ultimately gives you that the distance between them is actually increasing because you see this term right here as time increases, GT increases. 1/2 G stays the same, but you're basically going to have that GT term getting larger and larger.
Okay. So it would just be increases. It wouldn't be increases at first because I thought after a certain point, if you're going down, you would reach terminal velocity and then they would just kind of stay the same.
Now we actually by saying the acceleration is g, we've made the assumption that there's no air resistance, so terminal velocity wouldn't be an issue. But if you actually had taken that out, absolutely, you'd be right.
Oh, I didn't know terminal velocity relied on air resistance. Okay. I just
Yeah,
thought like once you accelerated so much, like you're okay, but yeah, that makes sense. With air
exactly.
resistance, that's what peaks you.
Yeah, ultimately, what it turns out, which we'll do in chapter 3, when we study air resistance, what we'll find is air resistance increases. It's always the force that's applied to an object falling in the air is normally like some constant times velocity. There's also cases where it's constant times velocity squared, but we're mostly dealing with constant times velocity. So at some point, what's going to happen is that constant times velocity is going to be so big that it cancels out the force mg. So that's when terminal velocity occurs. And in fact, you can find the formula for terminal velocity by setting uh, the constant times v equal to mg and then solve for v. That's the terminal velocity.
Okay. All right. So it would be increased. It would constantly keep increasing.
Yes,
Okay.
but you're absolutely right for thinking about I mean, for thinking about the terminal velocity. So that's a good physics point that you made there. So that's really good. In fact, in retrospect, I might would have put in there ignoring air resistance or uh, don't think about long term or don't think about terminal velocity or something like that.
Yeah, because I just kind of assumed like how they say it's in a vacuum and two objects jumped at the same time, reach the same around at the same time. So in my mind, they would reach the same acceleration, but it would just be a second apart. But I didn't take into account the fact that they would just ever increase in
Right.
speed. Okay, so let's see.
Yeah, you can see that's also a violation of relativity because obviously your speed eventually will reach not only bigger than the speed of light, but uh, after an infinite amount of time, your velocity would be infinitely large.
Mm-hmm. Okay, so this is the second one.
And that technique of using just general variables like X, G, T, that sort of thing. That's a good practice when you're trying to work out something analytically.
Mhm.
Is you can just let T represent any point in time. And if you can reduce it down to equations that you know are applicable, then you can do simple things like subtraction and get a function that lasts over time. It's really nice to be able to think that way. Not everybody thinks that way though. So, if I wanted to explain exactly why, I would not only analyze this, but I would also think about what does the equation x equals 1/2 at squared plus v0t get you? Because that it's really that squared or that cross term, basically when we square t plus 1 in parentheses squared, is that middle term that makes it differ. So it's an actual acceleration component, but it's a result of the acceleration for the extra 1 second allowed the velocity to be ahead by an extra 1 second. And
Mhm.
because of that velocity is always going to be slightly bigger than the other velocity.
Okay. Um, okay, this is the next one I had a question on if it's showing
Okay.
up.
Let me stop sharing in case it won't let you until I do stop sharing. So it's normally the way. Oh, there you go. This one, so it says figure 211 represents the position of a particle as it travels along the x-axis. What is the magnitude of the average velocity of the particle between 1 second and 4 seconds? Okay, now notice they're saying average. That's the key word. The other thing you want to notice they're saying is average velocity, not average speed.
Mhm.
The average speed would just be the total distance traveled, whereas the average velocity would be the displacement divided by the time taken.
Mhm.
So in going from t equals 1 second, it went from x equals 0 all the way to what looks like x equals 3, and then back down to x equals 2 by t equals 4 seconds.
Uh-huh.
So if you were doing the average speed, you'd want to say, okay, well, the object actually traveled a total of, let's see, 3 on the way up and then another 1 on the way back. So that'd be 4
Mhm.
meters total. Whereas when you're doing the average velocity, you'd say, oh, well, the final position is x equals 2 and the initial position is x equals 1. And therefore the displacement is 2 minus 1, which is just, of course, 1, and then 1 divided by 4 be somewhere around 0.25. So that's what I would say the right answer is the 0.25. And I see the red is what you were thinking. It sounds to me like you might have almost been thinking more about the average speed if you got 2/3.
Well, what I did is originally I got uh let's see, trying to remember how I did it the first time. To get the 1/2, I did 2/4 because I forgot to subtract.
Oh, actually, you did it right. It is 0.67, by the way. My fault. When I did 4 minus 1, I got 4, which is
That's what
obviously
I had
wrong.
done. Yeah, and that's what I did originally. Is I did it as if it was 0 to 4 seconds. I didn't think to. Yeah. So then when I did it again, it became I think what was it 2/3 or 1/3?
Yeah,
No, 2/3.
Yep, that's it. So yeah, the 0.67 is correct.
Okay.
I'm just sitting there thinking, why did I get 4 in the bottom? It's 4 minus 1. So yeah, arithmetic can bite you in the rear. The slope of a tangent line at a given time value on a velocity versus time graph gives, okay. Yeah, the slope at a given time does give you the instantaneous acceleration.
And
Uh,
that's what I missed when I first read it was the given time.
Yeah, so yeah, they're specifically talking about not drawing a tangent line between two, or what they call a secant line between 2 points on the graph. They're trying to imagine a secant line which goes from one point to the other, but then that second point, that farthest point, would slowly get closer and closer to the first point. Or actually, you should probably look at it like maybe the first point gets closer and closer to the second point until the line just becomes tangent at that one time only, and that's what the instantaneous acceleration is. So yeah, you're right on your second guess,
Okay.
or not second guess, but your second deliberation.
And this one I eventually, it took me like 4 or 5 tries before I finally got what I believe is the right answer. But I also wanted to see just how you would work this out as opposed to how I did it.
Gotcha. Says the acceleration of an object as a function of time is given by 3t. Ah, okay. So this is exactly the kind of problem that I wanted to work for my students anyways. So I did one in the last meeting. Actually, it was a class you were in, that meeting we did the other day.
Yeah, I
Um,
screenshotted the your work and was using that as an example.
exactly.
But the difference was is yours had given an initial X value essentially.
Yeah. Yeah, exactly. Which, if you need the X, you're going to have an initial X value. But if you only need the velocity function, then you never need that X value.
Yeah,
That's
and I believe there is another one I have a question about a little further on that's exactly this one, but it asks about displacement.
all right.
And that one I couldn't figure out what I was supposed to do at a certain point.
Let me write down this information. So it says V at t equals 0, which is what I'm going to call V0, uh, is equal to 0. That's the first piece. It says if the object is at rest at time t equals 0.00 seconds. And now they're asking what's the velocity V of t equal 5.00 seconds. So you can tell from this one that they've only given you one initial condition, and that means you can only integrate once. So that's
Uh,
one thing you should think about yourself. So, because otherwise you're going to feel like you did, like, well, crap, they didn't give me that initial position. But if you don't understand that the reason you needed that extra position was to make the second integral, then it seems like it's unsolvable, but it's not. So what we're going to do is we're going to say, ignoring the units, I'm just going to say 3t is equal to dv dt. Oops. 3t is equal to dv dt. Multiply both sides by dt.
could
So
you also bring up yours so I could see?
yeah, that was me. That was me thinking I'd already done that, which I clearly have not. So,
Yeah,
but
I
I'm
also had to go
good.
back and like look at my Calc 1 stuff because it's been a little while since I took calculus and I remember derivatives, but for the life of me, it feels like I never learned integrals because it looked foreign to me when you started doing it.
Yeah.
And it's only been like 5 months since I've done it, but apparently in that 5 months, my brain completely dumped it.
Yeah, it's easy to do that, especially if you haven't been keeping up, or if you had any little part that you didn't understand that well. Sometimes that can just make your brain draw a blank slate every time you come up with the idea of integrals or derivatives or whatever. So yeah, that completely happens. Luckily, as a teacher, this is part of the reason I am a teacher, is I just love having these ability to do this in real time, because I have to do it literally almost every day. But if I
Mhm.
wasn't doing it every day, I'd be just like you are, I'm sure.
Yeah,
So,
I was forced to take this summer semester off because not enough people signed up for the class, and we didn't find out until a week before, so it got
oh,
dropped.
gotcha.
So I didn't have enough time to sign up for another one.
Gotcha. Were you taking that this summer here at TCC or somewhere else?
Yeah, this summer it was going to be another engineering course, so
Gotcha.
not enough people signed up, and by the time it was too late for me to sign up for anything else.
Gotcha. So I just took the 3t and set that equal to dv/dt, because 3t is the acceleration, acceleration is dv/dt.
I'm still
And
not seeing your
it's still not showing for you.
no.
Uh, take yours off. It might be making you just look at your own. So maybe if
All right,
you,
I did stop share because I saw it earlier when you were doing it.
okay, I'll reshare. How about that? Let's do stop share again. And now do share again.
There it goes. It's starting to share.
No problem. So what I have written in blue was basically the equation. I'm writing in red so you'd see what action I took. So I'm multiplying both sides by dt, and now I'm integrating both sides. And you can choose ranges of integration to integrate there to skip the addition of a constant. But sometimes I find it's easier that students understand it better with the integration constant. So I'm just going to integrate it
Yeah,
both.
I saw a video where they were doing that with the like the small, I can't remember what they're called, the small numbers on top of the integral sign.
Oh, right. The exponents.
Yeah, but he wasn't showing all the
Oh, that.
steps, so it just made it more confusing.
Gotcha. Well, if you integrate 3t, that becomes 3 halves t squared plus, let's call this constant c0. And then if you integrate the integral of dv dt, that just gives you v. And again, you're supposed to have plus a constant of integration. So you can just put that on there. And then you can rewrite, oops, then you can rewrite it and say that v is equal to 3 halves t squared plus. Now, what I'm doing here is I'm going to subtract C1 from both sides. And then I'm going to say C0 minus C1 is just equal to plain C, or I'm going to define it to be plain C. And that just makes it easier because you're allowed to do whatever you want with those constants. You just have to make sure they fit the data. Now that we have a particular constant, we can now evaluate what they told us about that constant. So we know, for instance, v of 0 is equal to 0, and that tells us 0 is equal to 3 halves 0 squared plus c. So you see what I just did there?
Mhm. And
So
then
that
you would solve for C, and which would become 0.
exactly. So now what you know is v of t is just equal to 3
3
halves
halves.
t squared.
Okay, so that's, and then you would just plug in the information given, which is the 5 seconds, and solve it that way, correct?
Exactly.
Okay, so I did finally end up doing it right.
Yep. So that'd be 25 times 25 over, well, times 3 halves, that'd be 75 over 2. So that'd be what, 35, 37.5.
Yeah, that's what I got. So I also had a question again. Over the time, a lot of this stuff just left my brain.
Yeah.
The original notation, the 3t dt equals dv dt. How come it becomes dv dt?
That is our definition of instantaneous acceleration.
Okay, so they're saying this is the definition, and then this is the definition with the information we've been given.
Exactly. So dVdt is also a function, just like v of t is a function, just like x of t is a function, just like a of t is a function. It just happens that a of t is also equal to dv dt. So you can take 3t and set it equal to dv dt.
Gotcha. Because the slope of a velocity over time graph is acceleration.
Exactly. And more specifically, the instantaneous acceleration. That's why we know it's a derivative instead of the average.
So that's the okay. So instantaneous is the, or I'm sorry, instantaneous is the derivative. Average is the average.
Yeah. Or one way of thinking about it is the instantaneous is the limit of the average. So that's what ultimately turns it into a derivative. You're taking V2 minus V1 over T2 minus T1, but you're slowly
As it approaches
allowing.
zero, you're getting as close to zero as possible.
Exactly. And you can do that. We started with A here, but you could also do that with V. And you just say, if they gave you V as a function of time, you could say V of T, which might be, 3 meters per second squared times time. You could say that's equal to dx dt.
Mhm. Okay. So yeah, I ended up doing that one right eventually. I'm gonna go ahead and skip to the one that was almost exactly like that one, but it had displacement involved.
Okay, let me stop sharing for you then.
Um,
Yeah, so they can follow that up. If they gave you one more piece of information on that last question, like if they gave you another velocity at another time, or if they gave you a position at time t equals 0, or a position another time, that would allow you to do the next integration to x of t.
Okay.
And I think, like I said, I'm making the argument that you could do it with another velocity time, but that might not be the case.
All right.
There'd be some ambiguity in it. But either way, you could get the x of t, and then they could ask you a whole plethora of questions like, what's the average velocity between here and here? All right, what's the average speed between here and here? All right, what's the instantaneous velocity at this time? What's the instantaneous position at this time? So there's a lot of different questions we can ask. All
Mhm.
right. Now
Is
it
it
looks
showing
like,
up for you?
yeah, the acceleration of object function of time given the same function, I guess. If the object has a velocity of 1 meters per second at t equal 1 second, what is it? Yeah, this is a good one. So let me write this information down again. Might be able to fit it on the same block I had. So I've got a of t is equal to 3.00 meters per second cubed times t. And what we know is v of t equal 1.00 seconds is equal to 1.00 meters per second. Okay, what is the displacement of the object from t equals? The acceleration of object is given as a function of time. If the object has a velocity of 1 meter per second and t equal 1 second, what is the displacement of the object between? Okay, so they want to know delta x between which would be x2 minus x1, which would be x of 4.00 seconds minus x of 2.00 seconds. Okay. All right, so let me share my screen real quick. You might want
I'm gonna see if
to
pausing
your
it will.
screen.
I
Yeah.
paused mine, so I'm gonna see if that'll work.
Now, what might be happening, because it does say something weird when I set the thing to allow you to share your screen, it
Mhm.
says allow more than one person. So it might be something where you've got more than one screen you can click on to look at. And one screen would be you looking at your picture, and another screen might be me looking at, or you looking at my picture. But I'm not sure. I don't see anything that jumps out at me that shows me that's the case. So,
Oh, okay. Yeah, because the first time we did it, it worked fine, and then it just hasn't wanted to work right since.
gotcha.
All
Are
right.
you able to see my
Yes,
iPad
I see
now?
it.
Okay, cool. So that's, whoa. Yeah, I don't know what I just did. Okay, that's cool. I'm feeling better now. My my desktop just went crazy from a Mac standpoint. They've got a little button. If you push it, like all the windows disappear and like right. So again, I'm going to start with the idea that 3t is equal to, and actually I should give myself a little bit more space. I'm going to say 3t is equal to dv dt again, multiply by dt on both sides, and then integrate both sides. And this is going to give me 3 halves t squared plus, or excuse me, yeah, plus c 0 is equal to v plus c1. And then the fact that v of 1.00 is equal to 1.00 meters per second tells us that this time I can say v is equal to 3 halves t squared plus c. So I did the same thing I did earlier where I combined c0 minus c1. And what we're going to do now is say that 1.00 meters per second is equal to 3 halves times 1.00 seconds squared plus c.
Yep, I did that. I got -1/2.
Yeah, that sounds about right because you get 3 halves plus c is equal to 1. So c equals negative 0.500. And obviously that would ultimately have units of meters per second.
Uh-huh.
So now we can say that v of t is equal to 3 halves t squared minus 0.50 meters per second. Of course, the units of 3 halves are meters per second cubed. But the main thing is you can now see there's nothing else you can do. You could, in principle, for instance, take 3 halves t squared minus 1/2 and set that equal to dx dt, which is the next step. And then when you do that, you multiply both sides by dt and integrate like that. And that actually works, but you're left with an integration constant that may or may not pan out.
Yeah, and that's where I got to because C did not make sense when you solve for that.
Gotcha. So this should give us ultimately 3/2 as t squared is going to become 3/6 t cubed
Yep.
minus 1/2 t plus some constant, let's call it C0, is equal to x plus some other constant, C1. So you can say x of t is equal to 3/6, which is 1/2 t cubed minus 1/2 t plus some new constant.
Yep. Okay, I got that. So I was
That
doing that
looks
right.
like you can't do anything,
And
right?
that's where that's the last thing I did. I got to there and I could not figure out where to go from there.
So here's what is kind of cool. It may or may not allow it. So we're gonna see. That was 1/2 minus 1/2, right? Yeah. Plus c. That's going to be your function. And what they're asking us for specifically was the displacement. So they want x2 minus x1, which I said was delta x, which I also said was x of 4.00 seconds minus x of, was it 200 seconds?
Yes.
2.00 seconds. So all we can hope right now is that that constant cancels out from the subtraction. If it does, then we've got it. So I can now put in 1/2, which notice is a common factor of 1/2. So I'm going to say 4.00 seconds squared minus 4.00 seconds. Make that a square bracket. And then
So where's
plus
the 1/2 coming from?
C. Oh, I just recognize that there's a common factor of 1/2 here and here. So I just pulled that in front and said,
Oh, so you're just putting 4 seconds in as T right now.
right.
I got you.
So
Okay.
that's another way of stating the function. Just to, all right. So that part is just the x of 4. Now I've got to do minus. I should probably stick
Is
some.
it should be 1/2 T cubed.
Oh, cube. Thank you. Yeah. Thanks for catching that. Because that'd definitely give us a wrong answer otherwise. So now I'm doing the same thing. I'm going to say 1/2 of, this time it's going to be 2.00 seconds cubed minus 2.00 seconds, and then plus c. So you can see, or actually you can see here what's going on is the minus c with the plus c is going to cancel out. So we didn't actually have to have that integration constant. We should be able to work it out. And in fact, it's going to be, this would be 64. No, 4 times 4 is 16 times 4 is, yeah, 64. 64 minus 4. And then this would be 30 because it's 1/2 of that. So it'd be 30 minus, now in this case, it'd be 1/2 of 2 times 2 times 2 is 8. 8 minus 2 is 6. 1/2 of 6 is 3. So we get just 27. Yeah, it should just be 27. What were the answer choices it gave us?
27 is one of them.
Yeah, that should be the right answer. Is that what you got when you figured out what was going on?
I never got that far.
Okay.
I
You
got
see how
to
the C just disappeared?
okay.
Does that make sense that it
Yeah,
disappeared to
I'm
you?
writing it out now to see where I might have messed up. Okay, so the way I didn't do it all in one equation. I find it's easier for me if I solve like the 1/2, the 4, solve
Well,
that, then
right,
solve the
yeah.
second part.
Yeah, that's not a
So
problem.
what I would have got was 30 plus C minus 3 plus C.
Exactly.
But my mistake would have been that I didn't put them in parentheses, so I didn't distribute the
The negative.
minus sign, which didn't cancel out the second C, make the second C negative.
Exactly.
So I would have gotten just 27 and then plus 2 C's essentially.
Yeah, and you can't do that because you don't know what C is, but since it luckily subtracted, it would be fine. Uh, so yeah, that's basically how that works is sometimes you're lucky enough to have the integration constant not matter. And if that's the case, then you can do it even without the extra data.
Okay. So yeah, that one gave me quite the headache. All right, so I can go back and show you some of the other ones that I was having issue with.
Okay, I'll stop share.
All right, is mine showing back up for you?
Yep.
Okay, so this one might be a little tall. I might have to zoom out for a second. I'm stuck.
Which of the following graphs could possibly represent the motion of a function of time of a
Oh,
free
sorry.
fall object? Gotcha. But this is a motion as a function of time. So this is y or x versus time. Okay. And you already got one wrong, and it was that dotted one, the second one down.
Yeah.
Okay. So one thing they tried to get you to learn the other day, remember when they were asking you in that homework set if the acceleration is a constant, how is it related to the position? And they said x is proportional to t, x is proportional to t squared, that sort of thing.
Mm-hmm.
That's the same thing you're looking at here. So when they talk about a free fall object, you know the acceleration is supposed to be constant. The fact that we're saying free fall means we're ignoring air resistance.
Mm-hmm.
So when you say free fall, we're ignoring air resistance. That means the acceleration is just g, which is 9.8 meters per second every second, downward. And if you integrated that twice, the first time you get velocity is proportional to t, since if you dropped it, of course. And then the second integral would give you position is proportional to t squared. So you'd see that actual third one, the one right above the circle, is an applicable answer.
This one.
Next one down, the parabola.
So that's what position would look like.
Mm, yeah, it could. I mean, this is one where an object was thrown upward, it reached some max height, and then fell down and reached the original height at 7 seconds, and then continued to fall downward.
Okay, because I thought if we were just dropping an object, it would, then you can see I circled this one because I figured the position was going from high down to 0, and then it just kept going. So I figured it'd be
Right, but remember what the position when you do a position versus time graph, which is what that is. What's the slope of position versus time?
velocity.
And this velocity is negative and constant. Do you see that? The one you circled is negative and constant.
Yes.
So we know free fall is an actual accelerated motion, so the slope has to change of a position versus time graph. And notice it did say free fall. It didn't say anything was dropped, though. It says could possibly represent the motion as a function of time of an object in free fall. Object in free fall is an object thrown straight down as long as you study it only after it's left the person's hand, or an object thrown straight up, or an object just dropped from a height. All of those are fair game for what we call free fall motion.
And I added words that weren't there apparently. Um, and
Yeah,
see
or
these
you just
graphs, man,
instinctively felt like it meant that it was dropped, but yeah.
these graphs, even in the lab, these graphs, I am struggling with these graphs. Uh, Clearly I keep interpreting them wrong. So what would the one I originally circled, which would be the second one, what would this represent as
That's actually not a bad guess because I can picture you thinking, oh, the person held it perfectly still at 4 meters of height for like 5 seconds and then let go of it, or 4.5 seconds, and then released it and it started to accelerate downward. Because notice the slope is actually getting steeper and steeper, or a higher
So,
negative number. So
mhm.
that's actually not that bad of a guess. You just went on the assumption that basically it was holding perfectly still at 4 meters height for about 4.5 or 4 3/4 seconds or something.
Hmm.
So that wouldn't have been bad. The only thing is, like I said, you have to explain that horizontal graph. The same thing with the next one down. There's a horizontal flat spot that you have to explain. And the first one, notice there's actually a discontinuity. Motion doesn't take place like that, where it has an abrupt change in slope. At least that one's continuous. It's just its derivative is not continuous, but its derivative is velocity. That's a real thing. You can't have a discontinuous velocity. An object can't be moving at 80 miles per hour and then spontaneously start going at 20 miles per hour. And that's
Yeah.
basically what that's saying. Only it's worse. It's saying it's like it's going 1 meter per second, and then instantaneously it starts going negative 1 meter per second.
Okay.
So when you're looking at these graphs, think of the multiple things you know about them. Position versus time. You know the height of a particular dot on the graph is how far away it is from the origin. The slope at that point is the instantaneous velocity, and the slope at any 2 points with a secant line is the average velocity, is another way of looking at it. And thirdly, you want to realize that we're graphing velocity potentially, because the derivative of y with respect to time is velocity.
Mhm.
And therefore, the negative sign doesn't necessarily indicate a negative velocity. It means that it's a positive, or it's a velocity, but it's going in the negative direction. So keep that in mind when you're analyzing the graphs. Then when you do the velocity versus time graph, the same thing appears. The height above the x-axis is the velocity at any point in time, and then the slope is the acceleration at any point in time.
So then the one my second guess, the one I circled in red,
Mhm.
as a position versus time graph, what would exactly this represent then?
So if you're
This,
looking at that, it says it started off at 4 meters. And basically, it went from 4 meters above the origin to zero height after 5 seconds. So it did actually like fall, but it just went really, really fast from 4 meters to 0 meters at a constant speed.
so would this be like in the lab where you're using the, the the little device to measure on that rail, and
Yeah, yeah. If you
you
did that,
started it away from the sensor and then just let
exactly.
it fall towards the sensor?
Except I wouldn't use the word fall, because fall implies that at least the rail, as you called it, it's called an air track.
Yes.
At least the air track was tilted. It's in order for it to be quote unquote falling, you have to have a
Yeah,
vertical.
we when we had it on an incline and you just let go and it kind of went on its own.
Exactly. But this one would be more like, hey, I gave it a push, and because it's frictionless, that's why we pump the air through it to make it nearly frictionless. I happen to give it a velocity of zero point 0.8 meters per second in the negative direction. In other words, towards the ultrasound device, or towards the motion detector. And because it's frictionless, it maintained that constant velocity of zero point 0.8 meters per, or negative zero point 0.8 meters per second, and did that for the whole 9 seconds.
Okay, so this is a constant velocity. So that couldn't represent free fall because that's not exactly a constant
Yeah, because
velocity.
it's a constant acceleration is what free fall is.
Okay, and this third graph here, that could almost be this, but almost as if like you threw a ball up, but something caught it and then dropped it.
Yeah, it got caught in a thunderstorm and was held at bay for 4 seconds.
Okay. Yeah, I don't know why. I'm just having so much difficulty with these
No,
graphs.
I mean, it's a good thing. It seems like all you're doing is analyzing it, but you're just sort of missing a small part. So the fact that you're doing more than just gutturally responding with an answer you think, you actually look like you're thinking through it. So you've got half the battle won. It's just a matter of getting used to it a little bit more.
Okay. Let's see. All right. Yeah, the information I was finding in the book wasn't.
They
I don't think
they
given
don't
enough.
really give you much.
Yeah, they don't give you enough to solve these, and it was very confusing.
So whenever they say percent uncertainty, that's what I call in my class fractional uncertainty. But what it's done is you take the uncertainty, which is at least one in the last decimal place.
Okay.
Okay. So if you had a number like 5.6 and they ask you what's the percent uncertainty, you'd realize that that last decimal place, which is the tenths place,
Point one.
has to be at least an error of one there. So you'd say zero point 0.1 divided by 5.6, and that would give you the fractional uncertainty. If you then move the decimal two places to the right, that would be the percent uncertainty.
So for this one, you would do point one divided by 0.18, correct? Or 1.8.
If you were asked for what the percent uncertainty of 5.6 is, but that's not what they're asking you in this question. I just wanted to make sure you understood what
Oh
percent
yeah,
was.
the area
Yeah.
of the circle.
Yeah. So in this one, they're saying what is the percent uncertainty in the area of a circle whose radius is 1.8 times 10 to the fourth. So the area of a circle is pi r squared.
Yep.
Now
So
this,
pi times 1.8 times 10 to the fourth. Let's see. So I get 56548.667.
okay, I'll double check that just to make sure. A little slow on the uptake here.
I can't find my notes right now where I originally did this one to see what information I got.
Yeah, I got 1.01 times 10 to the 1, 2, 3, 4, 5, 6.
Oh wait, you know what I didn't do right there? I didn't square it.
Gotcha.
101,787,602.
101,787,5,160 is what I got. But I did 3.14159 times 1.8
Oh,
times.
I just did pi,
Yeah.
the symbol
Oh
for
yeah,
pi.
yours is probably a little better than mine. Only went to six sig figs, but that looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1.0179 roughly times 10 to the ninth centimeters squared. Now, what you're supposed to use at this point is sort of like your sig fig rules. So they're asking you what's the percent uncertainty in the area of the circle. So the area is pi r squared, and you just calculated that. But sig fig rules would tell you that you're only supposed to have two sig figs. So you'd have to call that 1.0 times 10 to the ninth centimeters squared. Does that make sense to you?
Okay, because yeah, I got when I did it, yeah, I got 1.017876 times 10 to the ninth. But then
So
yeah, I
round
wasn't
that to two sig figs,
okay. And how come it's going to two?
because the only operation done here is multiplication. And with multiplication or division, the number of sig figs is dictated by the number of sig
Yes.
figs with the factor with the least.
And I wasn't sure how that would work when I used like the pi symbol.
Now, pi, you actually carried it way more sig figs. So as long as you get at least as many sig figs as you have, you're good to go. So in this case, you'd have to use 3.1, but you did even better. And you should always go at least one sig fig higher. So if you're using 1.8 here, then you should have used at least 3.14, but you did even further. So you're golden.
Okay, so that
So
okay. So then
does
every
allow
round,
just two sig figs because the radius was to two sig figs.
so that would give you 1.0 times 10 to the ninth. So you would do end up doing, since it's to the 0.0, you would use 1 over or 0.1 over, or no, is it
Yep.
because that
0.1 over.
0.1 over 1.8?
No, 1.8 over or 0.1 divided by 1.0 times 10 to the ninth, because that's the area.
Oh, so you do it by the whole area, not 1.0.
Exactly.
Oh, okay. And see, again, by the book, it didn't give you any scientific notation examples. So I was just, or if it did,
Yeah,
I
and
skipped.
actually I'm bothered by it. So what is the percent uncertainty in the area of the circle whose radius is this? Oh, I see why.
So it'd be 10%.
Yeah, that should be 10%.
Okay. And see, what I did was I did point 0.1 divided by 0.18 or 1.8, which is what it gives you originally.
Right.
I didn't
Yeah,
do
when they're
it
talking
by,
about uncertainty, it's always that's supposed to be a quantity. When they say percent or fractional uncertainty, that's supposed to be a dimensionless quantity, and it's the unknown divided by the or the uncertainty divided by the unknown quantity with the exact same units. So that it's just a pure number.
so that should be 10%. Okay, this one I thought was going to be simple, but apparently not. Because
Okay.
I did the estimate the number of pennies that it would take to go to the top of an 8 foot ceiling, and I got that one correct. So I assume this one is to fill up a box that is 1 foot by 1 foot by 1 foot, so it's a foot cubed.
Right.
So I just did the radius of a penny, which I think was 0.75 times. I ended up getting 16 somewhere, and then I just cubed 16.
Gotcha.
Trying to find
So
my notes for this one. Oh, it's right here. Length times width times height. So 1 foot cubed. A penny is 0.75 inches. So I converted inches to feet. Um, so 0.75 inches to foot cubed is a very, very small number.
gotcha. Yeah. So what you did by doing that, you're dividing the volume of the uh well, you're sort of dividing the volume of the box by the volume of the penny, but that's more like imagining melting down the pennies so that they can take any shape you want, and then filling the box full of, copper and whatever, other metals they use, which obviously they just, do a plating of the copper. What you're wanting to think of here is imagine putting the pennies in the box. You probably would try to fit as many as you can most efficiently by being really OCD and making several little columns. So little pilings or piles vertical of pennies. So what you need is the diameter of the penny, which I'd estimate to be about 2 centimeters, and the thickness of the penny, which I'd estimate to be about 1 millimeter. And then you say, okay, well, how many can I fit in a length of 1 foot? So what you do is then say, okay, well, the number I can fit in 1 foot is 1 foot divided by 1 millimeter because that's how thick it is.
Yeah, I didn't take into account the thickness of it.
Yeah, they
I
want
just
you to
took
think in
into the
terms of stacking
diameter.
stuff. Yeah, that's another thing is when they're asking for how many fit in a volume, then you got to talk about volume, not area. So that's a whole another issue, but I figured you'd probably figure that out once you were advised about how you got to think, you got to physically think about stacking them the most efficient way you could. Do you think that you could fit more pennies in a 1 foot by 1 foot by 1 foot box by just throwing them in at random, or do you think you could do it better by
Yeah,
making
stack them.
individual stacks? Yeah, I
Yeah,
think
and I got
stacks
in
are
an
easier.
area you could get 16 across and 16 basically rows of 16
Oh,
is
okay,
what
so
would
that
fit.
means whatever number you get for the height, you just multiply that by 16 again, and that should give you the right answer, which I think was 5 times 10 to the 4th or something.
Okay, yeah, because I didn't take into account the thickness. So I just did 16 times 16 times 16, assuming that you could fit 16 up, but obviously you can't if you got to take into account the thickness.
Exactly.
So how would you do it when taking into account the thickness?
Okay, so what I'm doing right now is I'm taking the 12 inches that 1 foot is, and I'm converting that to centimeters because I know that 1 inch is 2.54 centimeters. So I can multiply by 12 over 1 by 2.54 centimeters over 1 inch. And that gives me 30.48 centimeters is 1 foot.
Okay.
Okay.
Could you share your screen again?
Yeah, I didn't write. I just was doing it sort of in my
Oh,
head.
okay.
I'll
Okay.
share the screen now. That's not a problem. I won't sure how quote unquote easy it was potentially going to be. So let me go ahead and share my screen. You might want to knock yours off before I put mine up, just in case
Yeah, I
you
paused
want
mine
to
again.
see. Are you able to see my screen now?
Um, no, it's not showing up like it's trying to load.
Might take a couple seconds, but we'll see. If not, I'll undo it and redo it again. Still not come up?
No.
Okay. So let me kill this again. I'm going to do stop share and share again.
All right, now it's showing.
Okay. So what I've drawn here is supposed to be a 1 foot by 1 foot by 1 foot box. Like that. And what I'm imagining is a penny has a diameter of approximately 2 centimeters and a thickness of about 0.1 centimeters. Now I'm keeping it all in centimeters. I could have said millimeter, but then I'd have to decide whether I'm going to make everything in centimeters or everything in millimeters or everything in inches. I'm going to go with everything in centimeters. So I decided to use the height as 0.1 centimeter because that's about a millimeter.
Okay.
All right. And then this, of course, is 1 foot. And this is 1 foot. And this is 1 foot. And what I found was 12 inches, which is equal to 1 foot, is equal to excuse me, is equal to 2.54 centimeters divided by 1 inch. And that's 30.48 centimeters.
Okay.
So that tells us 1 foot is 30.48 centimeters. Now what I'm going to do is imagine stacking pennies like this. And then how many stacks can I go left and how many stacks can I go right? So how many can I go that way? How can I go forward and backwards? And then, of course, how many can I go up? So up, I'm going to say 30.48 centimeters per penny. Or excuse me, per 1 foot. And then I'm going to take that and divide it by 0.1 centimeters per penny. By just putting per penny in there, it gives you units of pennies. So if I do 30.48 divided by 0.1, I get 304.8 pennies. So basically you can fit about 305 pennies vertically. And then I say, okay, well, left and right, I need 1 foot, which equals 30.48 centimeters. Now I want to divide it by 2 centimeters per penny because the diameter is roughly 2 centimeters, right?
Okay.
So when I divide that by 2, you get 15.24 pennies. And I'll call them penny stacks because that's how many stacks it's going to fit. So basically, I can do 15 pennies wide and 15 pennies deep. So total number of pennies equals 305 pennies tall times 15 penny stacks times 15 penny stacks again. So I'm doing 305 times 15 times 15. Whoa, I did plus in all cases, so I'm not sure why I did that. So 305 times 15 times 15 gives me about 68625. So basically, I'd say this is on the order of 7 times 10 to the fourth, which would say your book probably expects us to do 5 times 10 to the fourth. Because you
Okay.
really only care is my number, which is 7 times 10 to the fourth, is that 10 times bigger than their number, which is 5 times 10 to the fourth? It's not. Uh, what about is it smaller than the next number, which would be like 5 times 10 to the fifth? That might be one of the choices. It's not that big either, so the best answer is 5 times 10 to the fourth.
Okay.
And to be honest with you, 5 is probably right because I think a penny's a little smaller than 2 centimeters in diameter. I think it's closer to 1.8, 1.9 centimeters, something like that. So if I was being a little more strict, I'd probably come up with that. But to be honest with you, when we do these calculations, these Fermi calculations, it's the 10 to the fourth that's most relevant to me.
Okay. Yeah, and I guess if I had calculated in the thickness, I would have probably got the fourth instead of the third.
Yeah, you definitely would have got another factor of 10 roughly. At least you might have got a 10 to the fifth though instead, but it all depends. But the fact that you did do 16 by 16 stacks tells me that yeah, that was a good idea. You were at least thinking about how to do the calculation. And it seems like you rounded up though. I think you wouldn't you have come up with like 15.4 or 15.3 or something stacks.
Let me see. Am I trying? See, it's 0.75 inches in diameter. So I did 12, since 12 inches is a foot, divided by 0.75, and you get exactly 16.
Ah, that's why I got you.
So yeah, I did 16 times 16 to cover the bottom,
Gotcha.
which gives you 256. And then assuming that you could fit another 16 tall, I just did it times another 16 again, but that doesn't take into account the thickness.
Gotcha.
I was just thinking the
Yeah,
diameter. Basically, if you stacked them the same way you're stacking them on the bottom upwards, which wouldn't be as efficient.
exactly.
So yeah, I didn't take that into account.
So yeah, if we got 3, 9, 5, 4, 7, anything, any of those, what they call the mantissa, that's the portion of the scientific notation that's before the times 10 to the power.
Mhm.
That mantissa, that's almost irrelevant what that is, as long as it's not 10 or larger. And as long as it's not smaller than 1, that's all we care about.
Yeah, the
So
same order of magnitude.
exactly.
Okay. All right. So I'll show you the next one.
All right, let me unshare real quick.
All right. Are you able to see mine?
Yes.
Okay. So this is the next one, Adam.
Okay, an object is moving with constant non-zero velocity on the x-axis, the position versus time graph. So this is you didn't have me for lab, and I'm not sure what your lab teacher stressed on you guys, but what I tell my students when they're doing the analyzing motion lab as well as the motion detector lab is I want you to think of 3 questions when you look at a graph. And that means 2 different types of graph. There's a position versus time graph that we study, and then there's a velocity versus time graph. We hardly ever do anything with the acceleration versus time graph. So we just say those 2. But on a position versus time graph, you're looking at a graph, which is like some kind of line. What I want to know is consider a single point on that line you're graphing. What does it mean when you measure the height from that one little dot on the graph down to the horizontal axis, or if it's under it from the horizontal axis down to that one dot on the graph? What is that quantity? So that's something I want you to think about every time you do a position versus time graph. And another thing that you want to think of is at that particular dot on the graph, what does that slope on that position versus time graph tell us? And thirdly, what does the difference between it being a positive distance up to that dot or a negative distance down to that dot, what does that mean? And the same thing with regards to a positive slope or a negative slope. So those 4 questions are really important for a position versus time graph. And then you do the exact same thing for a velocity versus time graph. So on a velocity versus time graph, what is the distance measured from the horizontal axis to a point on the graph? And then what is the slope at a particular point on the graph? And then what do the negatives of those values mean?
So if I can go back to one of the ones with the graph, like, so the one that this was, where this was the correct answer, the
Right,
blue one. If I were to pick just a random point, say right here at 3 seconds, where it looks like it's about 4,
right.
that point would be it's whatever 4 units away from the above the origin.
Exactly, which would be the motion detector in the motion detector lab, or the origin that you chose on the video if you're doing the analyzing motion labs. But yeah,
And then so
what's the slope at that point mean?
well, the slope, I guess, where I picked would be 0 because it's changing direction.
Yeah, it's literally changing from a positive slope to a negative slope.
So your slope with your velocity at that point would be 0, but your
Yeah, and that's
acceleration
the
would
key
still
point.
be negative 9.8.
Right, but the key point is what you said, and therefore your velocity would be 0. That's the answer. The slope of a position versus time graph is the velocity.
Mhm.
So now also the fact that that point uh, was higher than the horizontal axis tells you that it's on the positive side of the origin. And what does the fact that the slope is, in this case, 0? But what does it mean if you chose the 1 second mark and the slope was positive?
That it's speeding up.
Not in this case, because this is a position versus time, and the slope
So
is what's the slope again?
slope is velocity, so that would just give you what the instantaneous velocity is. Or not?
Yeah, but
Is it instant velocity?
yeah, exactly. The instantaneous velocity at a point. Yep. But the big thing is the sign just indicates the direction.
Yeah,
So that means it's going in the positive direction at 1 second. What about at 5 seconds?
it would just be the instantaneous velocity, but it would be negative.
Exactly. So it's now going back towards the origin.
So on one of the ones where we did, you kind of start at the sensor and with the air track, and you go away from it and then let it come back. As you went away from it, it would become positive because you're going away. But then once
Exactly.
it changes direction as it's coming back towards it, it would then become negative.
Right. So that graph is actually a good representation of that. When you push it away from the motion detector, it went up to its max height, it came to a stop, and then started falling back towards the motion detector.
So basically, with if you take away air resistance and friction on both, the free fall in that air system would
Mhm.
mimic it would mimic free fall at that point.
Exactly. It just happens to be doing it slower. That's exactly why Galileo studied inclined planes, because he didn't have a timepiece that could study small enough time intervals for vertical motion. So he said, well, the trigonometry of it works out. So I can do inclined planes with very gradual pitches. And from that, figure out what the actual vertical acceleration would be if we did it completely vertically instead of just a small component vertical.
Huh. Interesting.
Okay. So now that you're thinking in terms of that those are just position versus time graph. The velocity versus time is another step away. And in that case, the velocity versus time, the distance vertically from the horizontal axis up or down is your velocity. And the slope at that point is actually your acceleration.
Acceleration. Yes. And it's
So
the
now go back to
instantaneous acceleration. Correct.
right. Yeah.
Okay.
And if that means if your acceleration is a constant, your graph has to be a line, because anything other than a straight line would have a changing slope and a
Yes.
changing
So
a
this
changing.
this
Yeah.
bottom graph would be constant acceleration.
If it's a velocity versus time, even though that's
Yes.
velocity versus time, but
If it
yes.
was velocity versus time, this would be constant acceleration.
Yep, exactly. So
Okay.
now look at the question we were doing. I bet you can figure it out.
Okay. So yeah, this is what I had changed my answer to.
Mm-hmm. An object is moving with constant non-zero velocity. Okay. So what do you think it
Constant
is now?
constant velocity means no acceleration.
A
So
straight line making an angle
so
with,
your velocity graph would just be a straight line,
yep,
which makes your position graph be a diagonal line.
yep. What you chose is perfect. No, we don't necessarily know whether it should be diagonal down or diagonal up. That all depends on which direction it's going, but they said a constant non-zero velocity. So it could be slope up or slope down, long as it's not slope zero, which is what the horizontal straight line would have been. So yeah, you got the right answer.
Okay.
So with these, this is good thinking. I didn't even realize I had one of these questions still left in there, and they're good. I didn't mean to take them out. It's just I didn't remember seeing them. So this can also be expressed in millimeters as uh, that's just a unit conversion away. So if you were to convert centimeters to millimeters, what would you have to do with the 0.00325?
You would basically it's adding extra zero because you're going from centi, which is 100, to milli, which is 1,000.
Thousandth, yes, yeah.
1,000,
I put a
yeah.
lift on my mouth for all my words. I don't know why I did that, but yeah. It goes from 100th to 1,000th. So yes,
So,
that's correct.
so you would get 0.3 zeros instead of two.
Ah, Uh, in that case, we're saying this is a very, very small measure of centimeters, but since the millimeters are smaller than a centimeter, it would be an even bigger number. So you'd actually expect to add a zero, not or excuse me, to subtract a zero, not to add a zero. Let me show you.
Let's say, yeah, because I ended up, I found, I don't remember what I found to get the correct answer. And that's what I was confused by is why were they subtracting a zero instead of adding a zero? That didn't make sense to me.
Go ahead and kill the screen. It's 0.00325 centimeters. And it's times 10 to the negative fourth or 10 to the eighth or negative
10 to
eighth.
the negative 8 centimeters.
Okay. So let me do this real quick. I'm going to share my screen. Uh, you're overthinking this one because it really is just a unit conversion. And I actually almost did the same thing myself. When I first saw it, I started thinking the same thing because I thought they were asking me to just make equivalent statements. So we have 0.00325 times 10 to the negative 8 centimeters. Is that correct?
Yes.
And we want it in millimeters.
Yep.
So if you used my mnemonic, if you did use that, you know you're going from here to here. And that, of course, is just one move. And the move is what matters, not the endpoints. Notice there was an endpoint there and an endpoint there, but the move is what matters. So what we're going to do is say 0.0325 times 10 to the negative 8 millimeters is right. But what I would do to keep from getting in that conundrum of making careless mistakes and overthinking it, I just write out 0.00325, excuse me, times 10 to the negative 8 centimeters. As always, I just try to put it over one so you don't get confused about where your numbers are in the fraction.
Mhm.
And then I'd say that 1 centimeter is equal to 10 millimeters because that's an equivalency statement. And that's, of course, true about anything that is one spot away. So, for instance, the dot to the right of the M there is exactly a factor of 10 different than the M. And then the C is one power of 10 different or multiplied by 10 different than the lowercase d. So that's another thing you should keep in mind. In this case, you, of course, just get that it's 0.0325 times 10 to the negative 8 millimeters. That's one way you could do it. You could also make the 10 be absorbed by the 10 to the negative 8. So you could choose to write this, meaning you're not changing the mantissa at all. I keep saying that word. If you chose to not change the mantissa at all, then you could have let the 10 actually hit that. Or like I did already, you could let it hit that. If I decided to let it hit that, then it'd be times 10 to the negative 7 millimeters. So either one of those is acceptable, but it's a matter of multiple choice. And what choices did it have as answers?
Well, now they want you to convert it to actual scientific notation.
Okay, gotcha. So now that completely gets rid of the argument I was making about how you could do either, because they both result in the same thing. What you do, for instance, if I took this number, I'd say 0.00325, the decimal's right there, and I have to make it times 10 to the, oh, they want it in scientific notation, right?
Yeah, so either one of them is going to become negative 10 because they're both moving to point or 3.25.
Right. So what I try to remind my students is that there's only one decimal place where you can put it where the value is between 1 and 10. It's actually allowed to be 1, but it's not allowed to be 10. So in this case, if I moved it between the 0 and the 3, it'd be 0.3, which is less than 1. That's not acceptable. If I moved it to the place between the 2 and the 5, it'd be 32. That's not acceptable. So I have to put it right here.
Mhm.
That is 1, 2, 3 decimals to the right, and that means times 1,000. Okay. So if you want to multiply the mantissa by 1,000, then you got to divide the exponent, the power, by 1,000. So we could say times 1,000 and then divided by 1,000. and you get 3.25 times 10 to the negative 10 millimeters. But you could also have done it with this other version the exact same way. You'd say 0.0325 times 10 to the negative 8 millimeters. And again, in this case, ooh, that was a really bad looking 0.3 there. So in this case, we're going to say I could move it here, but that gives me 0.3. I could move it here, and that gives me 3.2, which is acceptable. Or I could move it here, which is not acceptable. So I'm going to say X there and X there. And then we're going to say 1 and 2. So what I'm going to do is multiply this by 100 and then divide this by 100. And you get 3.25 times 10 to the negative 10th millimeters. So notice you get the same answer no matter which way you do it, and that gives you a little bit more confidence that you did it correctly.
Yeah, like you said, I overthought it at the beginning and was not making it as simple as just
The unit conversion.
start out by just moving the decimal one place to the right. That's how you get centimeters to millimeters, and now make it scientific notation.
Right.
I was
A big
basically,
part of what I wanted students to understand, and I sort of like them to discover it themselves. But what I just did here is a big picture of how I work with sig figs and scientific notation stuff. Is I always think I can never just randomly multiply a number by a number unless that number is one. So if I want to change the mantissa by moving the decimal 3 places to the right, then I got to move the decimal in the multiplier by 3 decimals to the left, just because, multiply by 3 decimals, or moving the decimal 3 places to the right is multiplying by 1,000, and then moving the decimal 3 places to the left is dividing by 1,000. Multiplication by 1,000 followed by division by 1,000 is the same as multiplication by 1. So it's nice to think in terms of these dividing the mantissa by a number and then multiplying the power by a number, or vice versa.
yeah, I'd never consider that either.
Yeah, it's one of those things. It's crystal clear once you see it, but until you think of it yourself, you sort of like, oh, I don't know what to do.
Yeah. All right. Let's see. And I'll show you. I guess I'll show you the next one I had.
You do have another one? Okay, let me stop sharing then.
Yeah, I did the practice test quite a few times, and there was some questions that I just, no matter what I did, I kept screwing them up.
Uh-huh.
Yeah, this one.
7 times X. Mm-hmm. Ah, so what they're saying here is X. Notice they said a person walks in a distance X northward, turns around, which means they're going southward at that point, and walks a distance 7X. So they went X minus 7X. That obviously gives you negative 6X. And if the total displacement of the person from the starting position is 400 meters, then what you're saying now is the total distance you are away is 400 meters. So you could say 400 meters is equal to negative 6X. But it's nicer and easier. I mean, you can think about it that way, and that's a quick and dirty. But go ahead and kill that, and let me show you a graphical way of doing it, so maybe it'll make more sense and look a little easier to you. So I'm going to go ahead and share my screen again. So I'm going to say, let's call this direction north. Let's call this direction south. And let's call this the starting position. or the origin. So we're going to walk a distance X. So let's say, I'm going to say that distance is from here to here. That's going to be X. Now I can go back. That's X, 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 X. I'm just trying to do this to keep it scale. I might not have made it big enough to do it scale, but I'm trying to in the case that I can, because that makes it even easier. But 1, 2, 3, 4, 5, 6, 7 is where we end up. Okay. And what they said was this distance was 400 meters. Okay. So just by me choosing, I chose unwisely. I should have chose one square, but I chose two because I thought I could fit it in, and I did mostly. But you see what's going on. By doing that, you can see that two squares represents X, and then two squares, two squares, two squares, two squares. I do that 7 times, and that ultimately gives me all 7X, and I can draw it graphically. Now I can figure out exactly what X is, which is what they're asking for, right? Isn't that what they've said? What is X?
They're asking what is the total distance walked.
Oh, the total distance walk. Okay, gotcha. So the total distance walked, you can already see, is X plus 7X. So that's 8X.
Yeah, it says the total displacement of the person from a starting position is 400 millimeters, or I'm sorry, 400 meters south. What was the total distance walked?
Yeah. Either way, we've got to figure out what X is, obviously. But you can now see that 6X is equal to 400. So we divide both sides by 6. And of course, that gives us 6 goes in the 360 times. So that leaves us 40 left over, and 6 goes in the 40 6 times. So that's 66. And that would be 4 left over. 66 and 4 6, that'd be 2/3. So 66.67. So the total distance traveled would be 8 times that. And I'm getting 53. That can't be right.
533, I believe.
Oh, yes. Sorry. I put in a 0, but evidently I accidentally hit the decimal place too. So it was treated as 6.0, and I mean 4.0 instead of 400. So yeah, about 533 meters roughly.
Yeah, and that's one of the choices.
But notice how the drawing helped. You didn't even have to know algebra to figure out that when you were able to do that drawing and do it to scale. So that's a big help. And it also is a graphical representation of displacement versus distance traveled. So when we calculate average speed, remember it's the total distance traveled divided by the time taken. So they'd want to, if you did the average speed, you divide that 533 by the time. Whereas if you did the average velocity, you would do 400 meters divided by that time.
Mhm. And I didn't consider that you had to walk the initial X before you started going in the other direction.
Right.
So I was considering it 7X instead of 6.
Right. Sometimes just drawing a picture helps you. And I almost always I draw a picture when I'm solving a physics problem. Very rarely do I do it without.
I'll show you the next one.
Okay, let me kill this. I got about 10 more minutes, I think, available. Hopefully that'll be a good start for you anyways.
Okay. This next one should just be making sure I chose the right answer on this one.
Which statement is correct about the relationship between average speed and the magnitude of the average velocity for any motion? Notice the keyword any there. That means if you find one contradicting fact to whatever answer you're going to do, then you can't use it because any implies all.
Mm-hmm.
You said the average speed is always equal to the magnitude of the average velocity. Yeah, I stressed that in class. I don't think I did as well stressing that in the in the online class as I did in the face-to-face one. But I did remember saying it one time. If you're asked a true false question and the true false question is true or false, the magnitude of velocity is the speed. You'd have to say false, even though most of the time that's a true statement, but there's very specific times where it's not, especially specifically when you're dealing with averages. And my example was the kid sitting at, playing t-ball. He hits the t-ball, steps on home plate. That's important for a cheesy reason, but still, he steps on the home plate, runs the first, runs the second, runs the third, runs the home plate again, actually touches the exact same spot. And you say, what's his average speed over uh, his path around the bases? His average speed would be 60. If we're using T-balls, I think they normally use 60 feet. So 60 times 4 would be 240 divided by, let's say, 10 seconds. So that'd be, or let's say, 20 seconds. So that'd be like 12 meters per second, which obviously is not running that fast. But if you wanted to do the average velocity, the displacement would be 0. So
Mm-hmm.
the average velocity would be 0. Now, in this case, you said the average speed can be less than, greater than, or equal to the magnitude of the average velocity. I don't think it could be greater than. That's the part that's bothering me on there. The average speed can be greater than, but I don't think it can be less than. That's what I meant. It says the average speed can be less than, greater than, or equal to. So yeah, when you're talking about speed, that at least the average seems to me it's always going to be bigger because it's the total distance traveled, and you're never going to have to subtract out some overlap or anything like that. So I don't think that one's exactly right. But the average speed is always 1/2 the magnitude. No, the average speed is always less than are equal to the magnitude of the average velocity. No, the average speed is always greater than. There you go. That sounds more like it to me.
But yeah, I didn't think of it the way you explained it just then.
Yeah, I'd say that that second answer is the best choice.
Okay.
2 meters per second for 60 minutes. Okay. He then turns around and walks north a distance of 3,000 meters in 25 minutes. Okay, so this is just like the problem I did in class. Remember average velocity, no matter what you've read about averages and what you've learned about doing averages with your scores and all that stuff, ignore all that. The average velocity has a very specific definition, and it's the displacement divided by the time taken.
Hmm.
So this man walked south at a speed of 2 meters per second for 60 seconds, or excuse me, for 60 minutes. That's 3,600 seconds. So that's 7,200 meters is how far he went, because you got to convert that 60 minutes to seconds, and there's 60 seconds in a minute, so 60 times 60 is 3,600. If you multiply 3,600 times 2, you get 7,200. He then turns around and walks north a distance of 3,000. So now he's 4,200 instead of 7,200 meters away, and it took him 25 minutes. So now the total amount of time is really 60 minutes plus 20, it's 85 minutes which you can divide or multiply by 60 to get seconds. So the total distance or the displacement in this case is 4,200 meters. And then you got to divide that by 85 minutes, but converted to seconds. So did you understand everything I just said there, or was it too confusing with all
Yeah,
the?
so you would get 4,200 divided by 5,100, correct?
That seems right.
Oh, okay. I forgot this. I did update this one. I forgot to change it. I did it again and I got 0.823.
2965 or something like that is the total distance traveled. Let's see. Did you get 0.823?
Yes.
Yeah, that's fine. 8235. So that should be around 824. So
All
yeah,
right.
that's
I know you say you don't have long, so I'm just going to go to the one that I had the most trouble with on these. It's this one.
okay. A 400-meter relay race, the anchorman, the person who runs the last 100 meters for Team A can run 100 meters in 9.8 seconds. His rival, the anchorman for Team B, can cover 100 meters in 10.1 seconds. What is the largest lead the Team B runner can have when Team A runner starts the final leg of the race in order that Team A runner not lose? So his rival, the anchorman. So I'm trying to figure out, I guess we have to make the assumption in this case that in the relay race, it's usually like one person, then they hand off to
Yep.
another, and hand off to another. I think we have to make the assumption that the last person that handed off to the anchor man, uh, did it at the exact same time as the other team. But you might actually be able to do the whole thing with not making that assumption, but I don't see an easy way to do that. So I think we have to go on the assumption that they were handed it at the same time. And what they want to know is what is the largest lead the team B runner. Oh, okay. So it is actually saying the largest lead.
Yeah. So they're not getting it at the same time. So they're
Exactly.
assuming B gets it first, and what's the largest distance he could be ahead and still lose.
And they're saying it in distance, not time. So that's another critical thing. Uh, and we're not taking the acceleration at all. So really all we're thinking is the team B runner takes 10.1 seconds to go 100 meters and the team A runner takes 9.8 seconds. So we just have to make sure the other person has a lead not bigger than a certain distance. And 100 meters at 10.1 seconds, which means 100 meters divided by 10.1 is equal to 9.90 meters, whereas 100 meters divided by 9.8 is equal to 10.0 meters per second. So in this case, we only have 100 meters they can run. That's really bothering me. Okay, what is the largest lead? Okay, so I think I'm gonna have to draw a drawing just to make sure. So let me do that. I'll write the stuff down and then I'll ask you to pull your
Okay.
picture down. So it says 400-meter relay race. Okay, okay, I wrote down the stuff real quick. Let me go ahead and try to shade this now. I'm gonna start wearing a hat. Top of my head's not that pretty. It's like, Jesus, who's that old man in this window? Clearly not me. All right, so I started drawing a picture too, just to help me and you figure it out. So if you notice, I drew like I did before. I decided to make up a unit and draw a scale drawing. So it's a 400-meter race, and you got, one person runs 100, the next runs another 100, the next runs another 100. So I showed that and represented each of those hundreds by two little squares.
Mhm.
And the purple is supposed to be what the faster leg team is doing. So the guy that has the final leg of the match, uh, does 100 meters in 9.8 seconds. I made them purple, and I made the other people in the red, and I showed them having a little lead when Team A gets their baton. So what we want to know is, what is that lead? So what we have to do is we have to say 100 meters by A has to be done in same time, and I should say or less, actually less time, as 100 meters minus X, where I'm saying X is the head start. So what we know is distance is equal to velocity times time. That's one way you can think of it. You can also think of it as velocity equals distance over time, something like that. We know it's displacement. I'm just using these words sort of roughly right now just to bring us back to one of our fundamental equations. And this is all about non-accelerated motion. We're only paying attention to assuming they're starting off at one speed and running the whole time and pretending like it's an average is their actual speed. So we're sort of making that assumption. But what we have done here is said we want the team A to complete 100 meters in the same amount of time or less as the team B does the distance that's smaller than 100 meters. So what we have there is the times are supposed to be equivalent. So or equivalent or less. So I'm going to see TA has to be less than team B. But team A and team B both have time given by distance divided by velocity. So dA over VA is less than or equal to dB over VB. Now, what I found was VA on average is 9.9, or excuse me, 10.20. meters per second, and VB average is 9.901 meters per second. And that gives me, of course, extra sig figs than I'm really justified in having. I only had 2 sig figs there, but that's basically what the average velocities are. So in this case, I'm going to take the distance that A has to travel, which is 100. I'm going to divide it by the velocity that A has, which is 10.204. I want that to be less than 100 minus X over 9.901 meters per second. So I can cross multiply and I'll get 990.1 seconds, because the 100 was meters, by the way. And this is technically also in meters. This has got to be less than 1020.4 meters. I'm cross multiplying here too, by the way, but now I'm multiplying by the 100, and then I got to distribute it to the minus X. So it's going to be minus 10.204 X. Do you follow what I did there, Dylan?
Yes.
Now I can, oh, that's supposed to be seconds, not meters, by the way. Which it's meters per second times meters. That's meters squared per second. Yeah, that's meters squared per second. And this other one should have been 9.9. Oh, that should have been meters squared per second. Okay, that makes a little better sense. And the X, of course, is supposed to have units of meters ultimately. And the 10.204 has units of meters per second. So yeah, that all works out. What I can do now is I can pull the 10.204x to the left-hand side, and I can subtract 990.1 from both sides. And when I do that, I'm going to say 102.04 minus 99.01, or excuse me, 990. 990.1. That looks right, right? Let's double check. Yes, yes, I had to move decimal 2 places. So I'm doing that subtraction, and I get 888.06 meters squared per second. That can't be right.
No, I got 30.3.
30 point. That sounds a lot better. I don't know what happened with
1020 minus 990.
Yeah. Oh, I see. Yeah. And it's 1020.4 minus 990.1. 30.3. Thank you. Oops. And that's meters squared per second. And of course, this whole thing right here would also have units of meters squared per second. So X is actually meters per second. So now I'm going to divide both sides by 1 point or 10.204. And of course, that has units of meters per second like that. And of course, that'll just give us just plain meters. So I'll say 30.3 divided by 10.204. And that gives me 2.96. So X is less than 2.9694 meters. Sorry, it took me a little while to figure out what was going on with that one. I hadn't seen that problem. I don't think I've ever seen that problem before. It must have been something I just haven't been asked before. But that looks like about the right answer. So he can get almost 3 meters ahead, but he definitely needs to be no more than 2.9694 meters.
And I believe when I searched that answer online, it gave the 3, but it didn't explain how it got there.
Yeah, that would I'd say 3 would be a reasonable result given the sig figs. Yeah, because you could do 2 sig figs because that's how many you had, and 2 sig figs rounds to 3.0. So yeah, that's right.
Okay.
Do you understand how we did it and how I set that up?
Yeah, I had made it way more difficult, but nowhere did I get close to any of those answers.
Well, I mean, I have a lot of experience doing this, and this is more like stuff we would have done in high school algebra 1. But that was a really long time ago. You think your calculus 2 was a long time ago. Yeah, look how long algebra 2 or algebra 1 would have been in
That
high school.
was in high school, yeah. So
Yeah,
over
that's the way they did it back then.
13 years.
Yeah. So if you look at it, that idea of distance equals velocity times time, or velocity equals distance over time, you can always see when you're doing these type problems, if you're lucky enough to have something like a constant velocity, or even there's a way you can do it with constant acceleration too. But the main thing is you have to realize that two of the movers have the same quantity. In this case, they both had to go 100 meters total. Uh, or in other cases, maybe they had to do it in the same amount of time, or in other cases, maybe they had to do it with the same final average velocity. But the main thing is you figure out what they have in common, which in this case, like I said, was the the time is what I wanted, not necessarily to be common, but less than. So I set it for the time, and then I just had to solve d equals v times t for time, and put that on each side.
Mhm. Okay. That's it for the questions I had on here. I did just have 2 other questions roughly about this work.
Okay, and
Um,
flip through those other ones. It might be quick answers I can give you with the little bit of time I have, and just not showing any work.
okay. Um,
But go ahead and what you thought about asking me, anyways.
um, so yeah, one of the other ones was just another one of those approximate
Uh,
uncertainty questions.
what is the volume and its approximate uncertainty of a sphere? So yeah, this is just like that other one, except now the volume of the sphere is 4/3 pi r cubed. So you got to use that. That's in the front cover of your book, which is some of the stuff I give you in the tests when you actually take the test. But in this case, you're wanting to again realize I got 3 sig figs, and therefore the uncertainty comes from at least a 1 in the last decimal place when I round it to 3 sig figs after doing the calculation.
Mhm. So
So
yeah, I did the
I'll do the calculation real quick and see if I can tell you what the answer is. 1.96.
yeah, I get 31.5, which is what they give you, but I was unable to get the uncertainty part.
Gotcha. So the volume I got was 31.5392.
Yeah.
Now, if I round that to 3 sig figs, that means the uncertainty is plus or minus 0.1.
Hmm.
So 0.1 divided by 31.53.
But this isn't asking for the percentage. It's just asking what is the approximate uncertainty.
Gotcha. So we still have to find the percentage first, just because we got to multiply that by the actual known value. So I'm doing 0.1 divided by
31.5.
31.5.
I'm getting 0.00317.
Yeah, 0.00317. That's good. So that's your uncertainty. If you wanted to make it a percent, it'd be 0.3, but we don't need the percent because what we're going to do now is multiply that by the 31.53 to get
Oh,
the uncertainty of the volume. What is the volume and its approximate uncertainty? Okay, gotcha. So we know the volume is the 31.53, and we know the uncertainty is 0.003. So in this sense, they're telling you you should be able to call it 31.5 plus or minus 0. It shouldn't be that. Well, let's see this. It does have other. Okay, so I'm going to take this 0.00317 and I'm going to multiply it by 31.53.
you get 0.1.
Yeah, I get 0.1, so it should be 31.5 plus or minus 0.1, but it said that's wrong, right?
Yes.
I think this one, the fact that we got no, that can't be right. I was getting ready to say the 0.00317. That uncertainty suggests that it should be rounded to 3 decimal places instead of 1, but that was bad arguing or bad thinking on my behalf. Uh, I suspect, I hope he's not doing this, but I think he is. What is the volume and its approximate uncertainty of a sphere of radius this? So what's going on here normally is there's a formula we're supposed to use for propagation of error. And this is basically a variable, our function that has exactly one variable. The volume is the function, the variable is the radius, and the volume function is 4/3 pi r cubed. So what it turns out is that the uncertainty in the volume is equal to the absolute value of the derivative with respect to r times the uncertainty in r. So if I took the derivative of 4/3 pi r cubed, you get 4 pi r squared. So that's the actual derivative. So the uncertainty in the volume is the absolute value of 4 pi r squared times the uncertainty in the r, which is 0.01. So if I took 4 pi r squared, so I say 4 times 3.14159 times 1.96. I know I'm doing calculation way more than you asked here. I just want to make sure I can give you the right answer up front. So times 1.96 squared. That gives me 48.275 times 0.01. Hmm, that can't be it either, huh? Yeah, I'm gonna have to think about this one. I'm not sure because he didn't give us enough information in the chapter 1, which is what this is based on. He talked a little bit about quadrature and propagation of error there. I'm gonna have to think about this one a little bit, and I'll let you know what I can find out. I might have to make just one as an example. Uh, in fact, let me do this. I might have to make up an example like this and work a problem in class, just or in class or online or something, just to make sense of it and propagate that out to you guys. So I'm going to say, I'm just taking a screenshot of it so I can remember.
Okay. Always feel good about when I get something wrong and it even stumps the teacher. So,
Exactly. That's a good a good sign that you're at least getting the hard stuff. Okay, so evidently putting that in a crazy spot there. Let me put it over here. Teaching stuff, go to my semester. Okay, so I've got that saved at least. So yeah, that one I need to think about a little bit because I'm not sure how far he's going with this, but I'll think about it a little bit and come up. So what other questions do you have?
um, since the due dates for all the stuff has been shifted, does that mean the due dates for chapter 3 stuff is going to get shifted as well?
The tests are definitely shifted. I'm not certain that I need to do any additional chapter homeworks. I'm sure I'm going to have to push chapter 3 back, but maybe not chapter 4.
Okay, because that's what I was wondering. Because 3 is due on Wednesday,
Yeah,
and
it definitely
I've
won't be right on
yeah,
Wednesday.
I've spent all my time still trying to work out stuff for chapter 2.
Yeah, the good news is chapter 3 is really good in that it really supports chapter 1 because you're just basically using those same equations more. So that will help you. But yeah, the chapter 4 is definitely not going to be due Wednesday.
For chapter
Bare
3.
minimum, it'll be due Sunday of next week, which I think is the 22nd.
Yeah, because right now it shows chapter 3 being due on Wednesday, and then chapter 4 being done due 2 days after that.
Yeah, suck it up, man. You gotta work a little harder than this.
I mean, if I'm luckily at my, I've switched positions at my job to where I have more desk time, so I've been doing a lot of work there. I can't imagine having to do all this stuff at home. I'd be never sleeping.
Yeah, yeah,
Um,
it's not
but
easy.
the last question is, the test is one that you said it's a take-home test, so we can do it online, correct?
Yeah, you're also allowed Google searches and notes
Okay,
and
how do we access that? I haven't seen it.
I just made it available today, early
Oh,
this
okay.
morning. So if you look in the
I guess I'll go ahead and
modules
stop
of
sharing it.
Canvas, you should be able to see it as a module called online tests.
All right, let me go to my Canvas real quick. Oh, okay. Okay. Yeah, I see that now. I hadn't it, yeah, if it was just made available today, that's why I haven't seen
Yeah,
it.
exactly. Basically, I have to go through when I go to make them. They transfer automatically from my old courses when I make new ones, but sometimes it just leaves parts out, and I have to go back and remake those parts in some cases, or just recopy them in others.
Mhm.
So that's what took so long. But now it's up, and I think the next one, the practice test for the next one's up as well with the appropriate due date. Notice the practice test is going to disappear on the due date of that test.
Okay. So yeah, it says September 22nd is the day the test is due. So the
Yep.
practice test is, yeah, it's going to be September 22nd.
Anything
Okay.
else? Any more of those questions you want to show me and see if I can give you a quick
No,
answer like I tried to?
those were all the at least out of all the practices, those were the ones that I got wrong and wasn't able to figure out.
Now, your first name did pop up on this video a couple of times. I've told my students, let me know if you don't want if you're have a problem with your name popping up on my YouTube channel. I am going to put this one up because we've solved a lot of problems. Is
Uh,
it okay with your name up there? Or
yeah, it's fine. I don't mind.
Okay, that's cool.
But yeah, I believe that's all the questions I have for
All
now,
right.
at
Well, you
least.
can send me photographs like you did in the past if you have any others what you come up with, but you can also ask me, of course, tomorrow in class.
Okay.
All right.
All
See
right.
you,
Thank you
Dylan.
very
Hope that
much.
helped.
Yeah, thank you.
Bye bye.